That's a very heavy lift.
Until it works with something like all.
Okay.
Yeah. Okay, 7.67.
And you're trying to be God.
Will you aim it for me, please?
So just and then I'll probably take it after I'm done talking. Okay.
So should I aim it at the chalkboard?
Probably at me while I start talking, and then I'll probably turn it around while I finish talking. Okay, folks. So hopefully you're all averaged. Let's go back to the beginning of the worksheet and kind of talk through what the mathematical equation tells us about this, and then compare it to our data and see what's going on. Because this is a hard lab to perform. Sometimes it can be a real challenge to get good data, so let's look at what we expect, what we saw, why that might be. It looks like we did number 1 and number 2, so let's start on number 3. It says label the diagram to show which parts of the apparatus are represented. So we did that. We have a mass, we have the radius, we have the centripetal force, which is provided by the washers. So that's all labeled, hopefully on your diagram from number 1, right? Number 4 says make a prediction using the equation, and that equation would be the centripetal force equals mass times velocity squared divided by r. What will happen to velocity when centripetal force increases? So we're going to assume that the mass stays constant, which you guys know to be true because you didn't change the little washer that was flying around. That mass stayed constant, right? And you didn't change the radius. You kept it right at that 6-inch radius, hopefully, right? So predict using the equation what will happen to velocity when centripetal force increases. All right, so if we use algebra here, right, and we know that mass and radius, right, form a constant, right? They're just going to be a constant number. So really what we could say is centripetal force equals some kind of constant times velocity squared, right? So it just said we're going to increase centripetal force, which is what we did. We started with 2 washers providing centripetal force, and we increased that to 4 washers, right? So if we increase centripetal force, I don't know, is that aimed? Mm-hmm. If we increase centripetal force, and this has to stay constant, right? Mass and radius stay constant. What do you predict would happen to velocity to keep both sides of the equation equal?
It'd be the same as the centripetal force.
Not necessarily the same because you have to multiply it by the constant. But if this goes up, what has to happen to that for the two sides to be equal?
It has to go down.
Has to.
Oh, no. Oh, it has to go down.
Take a vote. Who says up? Has to go up?
Let's go up.
Who says down? Okay, let's go for up. So think it through, right? If centripetal force increases, this whole side gets bigger. The equal sign keeps being true in an equation, right? This constant can't change, so to make this whole side bigger, that's the only thing that can get bigger. So when we increase centripetal force, we increase velocity. Okay, so in number 4, it says make a prediction, okay? So when centripetal force increases, our prediction is going to be velocity has to increase, right? So you need to write, when centripetal force increases, velocity has to increase. Remember we talked about direct proportion and inverse proportion. And since this is squared, you can't say that they're directly related. You can only say that that when one goes up, the other goes up, because this has to be squared. So it's not going to be like a straight line thing. When force increases, velocity should increase. So that's number 4.
So just like that?
Yes, in number 4. When centripetal force, the number of washers increases. Like when you went from 2 washers to 4 washers.
Okay, so write down when
The velocity of that little mass flying around should have increased. Number 5 says make a prediction using the equation about what will happen to the radius when centripetal force increases if we keep mass and velocity constant. So here's what that's going to mean. Okay. So the third thing that you're going to do that you haven't done yet in this lab, now you have 4 washers instead of 2, right? And hopefully you can see that the time it took was different from having 2 washers providing centripetal force to having 4 washers, right? So what would happen? Now you have 4 washers. What if you want the same time for 20 revolutions? Would you have to increase or decrease radius to get the same time? So this is a really tricky thing. Hopefully you're better practiced now at this rotational motion. But let's make a mathematical prediction before we try to do it so you have some idea of what to do. Okay, so we're going to keep mass constant, which is this little guy, right? You know, that always stays constant in this whole lab. And we're also going to keep velocity constant, right? You're going to try to make the time with 4 masses equal the time you got with 2 masses by changing the radius. Okay, so that over here, if we look at the equation again, same equation, right? So now we're going to keep mass constant and velocity constant, time in other words, right? So what has to happen to radius if force increases?
The radius will have to be shorter.
Right, so I'm going to solve it out this way, and I'm just going to call this constant K, because we're not changing mass, not changing velocity. So if force increases, to make constant stay the same, to make the equal sign stay true, to keep this side unchanging, when one goes up, what has to happen to the other one? Go down. Has to go down. Okay, so we're going to say the radius has to go down. Okay, so now you have a starting point to try to do the rest of the lab. When you've added washers here, to get the same time that you got in part 1 with more force, you're going to have to make the radius shorter than the blue mark. So that'll be really, really tricky. He should have done it backward, maybe.
That looks faster than what we got.
Well, it might be doing more rotations, but
Well, it has to do 20 rotations in the time that it took before. So
Can we just change our length to longer?
you'd have to redo the whole experiment. Yes, you could. And in fact, next year I might consider it. Or I might start with 4 washers and a longer length and then go to 2. I don't know. I don't like this. Last year was just chaos. It was really challenging to even figure out what was going on in the room. So you guys are providing me with a good way to observe this experiment and fix it, because it's not perfect. Yeah, you guys are my guinea pig class for this lab, because it was just bedlam last year. Okay, so let's turn over to the back page. Yeah. Okay, so on the back page, you guys filled out the first chart, right? And you got your time, but it says how did the so we're right here, kind of right below the chart on the back page. Okay, when centripetal force increased, what happened to time? So when you added the extra washers, did it take more time or less time for 20 revolutions? Less time, and that's what I would have predicted. Less time for 20 revolutions. Time should have decreased. If you didn't see time decrease from the first chart to the second chart, raise your hand and we'll figure that out. So you guys, it actually took longer with 4 washers?
Yeah. It did. Because it was boring out.
You guys, how about, what was your first chart? Less? Okay. So it should have taken less time. So we have some sort of error going on. So if you are in a group where it actually, time didn't decrease when you added the washers, you need to write like a little thing next to your chart, like there's some kind of error here. Time should have decreased and it didn't. And then ideally, if we had lots of time, we would go back and figure out what that error actually is. And I would go over there and watch you swing your washer and figure out where the problem is. I'm not entirely sure though.
I think like maybe it was a little longer than the blue mark, would that make a difference?
That might make a difference. Yeah. Or if your velocity wasn't constant, like if you're kind of like slow, eek, slow,
Our
fast.
velocity looked pretty,
Look pretty
on point.
constant.
yeah, but
Maybe if you're going slower, like on some.
What, do you have a metal tip pen? See,
Yeah.
that should be good. The metal tip pens don't have a lot of friction. Some of these pens, you get enough friction that you actually don't really have to keep a super constant velocity because the friction keeps it from sucking it in. So you can actually go much slower than you really ought to be able to. But those metal tip pens work the best. So,
yeah.
are you supporting the string with your hand right there?
Oh,
Okay.
I wasn't doing it this year.
Okay.
So I could have been. When, I mean, I didn't need to do it though. I mean, it depends how you hold the pen. You were holding like this though. Yeah.
So that's
I was
good.
holding like that.
Yes.
But I never did it. I never did it. I just counted.
Okay.
So I don't know.
Do you think you had trouble counting the 20? Like seeing it go?
I
It's so fast, it looks really
It
hard
did
to me.
seem, yeah. I don't know.
So we can hypothesize about error, but if you're in one of those groups, just right here, it should have decreased, it didn't, there's some kind of error going on. And actually there's a hole for that. So here, how did the result compare with your prediction? If your time actually did decrease, that's good. If time didn't decrease, then you need to say some sort of error is going on. And you can take a guess at what that is. If you were bad at swinging, bad at counting, supporting the string, I know, not hitting Jesselyn in the head with the thing. So fill in that blank right there on the back of the paper.
Do you say decrease?
It should have decreased, but it didn't.
So
Yours
error.
increased, so some sort of error happened. And then you can guess at what that was. Like, do you think it was an error in timing, counting, swinging,
Okay.
supporting the mass, not keeping the radius right, not keeping the velocity constant? You can all lay down your lab apparatuses.
Such a funny word, apparatus.
Yeah.
It sounds like appendix. I don't know why I think about it.
Some sort of, how do you spell it?
So weird. I always think you're saying that when you say apparatus.
Oh no.
Appendix.
I just think breathing apparatus when she says apparatus. I think
And then there's me who has no idea what she says.
Oh no, do you have to have like breathing treatments? Oh,
I think Darth Vader.
oh you. That's scary. Okay, so once you've written that, whether it's yes, it decreased, hooray, or oh no, there's error, what could it be? It goes on to say, now for the third part of the experiment, try to find a radius at which you can swing the apparatus with 4 washers, so the time for 20 revolutions equals the same time it took during part 1. So here's where, if you had error, you guys split up and join another group.
Okay.
Yeah. So, like, you guys can swing washers with them, and you girls can join them, and then we'll have a group of 3 and 2 groups of 4, and that's fine. So, what you're going to try to do, though, I get to hold an apparatus, is you're going to try, like, say, when you had 2 washers, this thing, when you had 2 washers, how long did it take to swing it 20 times? 6 seconds?
Like 6:30.
Okay, so like, let's say it was 6 seconds, right?
6.
So I want, now that I have 4, it takes less time, right? So I need to change the radius so it does take the whole 6 seconds now, right? I want to make the time with 4 washers equal to the time with 2 washers. So we just predicted that when we've increased the force from 2 washers to 4 washers, we're going to have to decrease the radius, okay? So you're going to have a radius smaller than that 6 inches. So see if you can get I don't even know if it's possible to swing this with 4 washers in a radius of less than 6 inches without getting it. You have to go so fast that it just gets sucked right in. But try. And see if you can do it. And I'll give you 5 minutes to try. And if you can't do it, that's fine. But give it a go.
Hiya.
You've made a good prediction, at least.
No, I've made a prediction.